Good evening, colleagues. I would like this evening to welcome you at this auspicious occasion of the inaugural lecture of our colleague, Professor Zenixole Tshentu. I want to greet the Deputy Vice-Chancellors, Professor Andre Kiet, the Deputy Vice-Chancellor for Engagement and Transformation, DVC for Learning and Teaching, Professor Cheryl Foxcroft, DVC for Research, Innovation and Internationalization, Dr. Thandi Mgwebi, all the executive deans of faculty that are here represented. I particularly want to greet the acting executive dean of the Faculty of Science this evening, Professor Eileen Campbell. I want to greet all the colleagues in the Faculty of Science. They've turned up in numbers, as well as the HOD, Dr. Buyiswa Hlangoti, and colleagues from the Department of Chemistry. I want to greet all professors and all members of the Academy in its entirety. Members of senior management, our students, undergraduate and postgraduate students, honored guests, ladies and gentlemen, family members, friends, and colleagues who are sharing with us in this celebration here as well as online. I also want to recognize a special guest of our university that we have here this evening, Miss Liz Ngonzi, who is our partner at the university. She's the founder and director of the Social Impact Institute in the USA. I am also pleased to welcome you all colleagues that are collaborating with Professor Tshentu in his journey, who are here and who are not here, who are all over the country and all over the world. I welcome you to this lecture this evening. I particularly wish to single out and acknowledge and welcome Professor Tshentu's family and friends. Especially, I want to recognize his wife, Nolita Tshentu, and his children, whose constant understanding, encouragement, and support through periods of intense academic duty and absence have enabled this illustrious academic milestone and achievement for our colleague. I want to welcome you this evening. I want to recognize Professor Tshentu's mother, Miss Nomapati Tshentu, who is also joining us online, and his father, Professor Mncedisi Somniso, for ensuring that he remained focused throughout his academic endeavors. And to Prof. Somniso, who is our colleague, we say welcome back, Professor, to your alma mater. I also want to recognize Professor Tshentu's mother-in-law, Mrs. Mkoto, whose willingness to take care of the children, of the grandchildren throughout this journey, alleviated work pressures and contributed to the attainment of this milestone. In an African idiom, we say it takes a village to raise a child. A warm welcome is also extended to Professor Tshentu's friends and colleagues and collaborators, especially those in the Faculty of Science and the Department of Chemistry, who have supported and encouraged him on this long journey. Professor Thomas Gerber is acknowledged for his invaluable guidance throughout Professor Tshentu's postgraduate studies, as is Professor Jan du Preez for his role in ensuring that Professor Tshentu remained in chemistry when he was a final year undergraduate student, then changing his trajectory for good. All of you, I am sure, take much pleasure in witnessing this realization of the potential of our colleague, which in true academic spirit and academic stewardships as senior professors you helped to nurture. The support of family, friends and colleagues resides at the center of our success as individuals and as professionals. They keep us grounded. They are our safe harbors, our shepherds, mentors, and at times, our disciplinarians. This evening, we also acknowledge and salute all of your various contributions. Ladies and gentlemen, it is always a matter of personal pride and pleasure when one of our own is acknowledged by their peers and the academic community. This is especially so when their life's work is so relevant to the challenges facing our country and our continent, and so consonant with our striving to promote the public good while making our mark, amongst others, through life-changing, student-centric educational opportunities, innovative research, and transformative engagement that contribute to a better world. I felt I should mention that because it aptly captures our own institutional aspirations and ambitions. This evening is no exception. Professor Tshentu completed all of his studies through this university and is now plowing back to the benefit of our students, sister institutions, the community at large, as well as society, through his teaching and his research and collaborations. I just had a short conversation with the professor outside when I said that just as you being promoted to the full professor, we have also taken up the role of being the deputy executive dean. And then he said, but I'm looking forward to this because this is about largely recalculation. So I really wanted to lead this. So thank you very much, Professor, for that. His loyalty and commitment to excellence and impact have resulted in him rising through the ranks from being a junior lecturer in 2005 to his current position of Deputy Dean, as I've said, in the Faculty of Science. Professor Tshentu's work is scaffolded by formidable academic accomplishments and exemplary teaching, professional and publication records, as well as various forms of engaged scholarship and collaborations. This is a testament to his enduring commitment to expanding the body of work in his field and discipline while making sure that it finds practical expression and relevance in our efforts to contribute to the flourishing of our country and the continent and the globe at large. It is in this context that Professor Tshentu's work assumes such importance as a timely reminder that South Africa does indeed have tremendous potential and can be the architect of its own flourishing future. We are honored at this point in your career, you are part of Nelson Mandela University family. I am acutely aware that you could have gone anywhere. Again, I want to personally thank you for taking up the daunting role of being the Deputy Executive Dean. We are proud of your accomplishments, Zeni, and we eagerly look forward to listening to your lecture tonight. We congratulate you on your outstanding achievement. Being promoted to the level of a full professor is the definitive affirmation of scholarship by your colleagues. I now request the Acting Executive Dean of the Faculty of Science, Professor Eileen Campbell, to introduce Professor Tshentu to the congregation. Enkosi, ngiyabonga, danki, manzenethol.
Good evening to each one of you. It is a particular privilege to stand here today to introduce a colleague and a friend. Zeni, as we know him and love him, has very much become everything we admire and love about the Faculty of Science. And so I'm humbled to stand here before you today. Professor Tshentu completed his doctoral studies in inorganic chemistry in 2005, focusing on the coordination chemistry of rhenium. He obtained his degrees at the former University of Port Elizabeth, and during his PhD studies he was employed as a junior lecturer in our Growing Our Own Timber project, and that makes it even more rewarding to see him rise to this level. After that, he went to Rhodes for a few years as a lecturer and then senior lecturer. And after 7 years there, he returned to our university as a senior lecturer, as an associate professor, as an associate professor. He has been the head of Department of Chemistry from 2016 to 2018, and the director of the School of Biomolecular and Chemical Sciences from 2019 to 2021. As the VC has mentioned, from May this year, he has become our Deputy Dean. I just want to pause from the biography to tell you that I was the faculty representative on his appointments committee, and I had the privilege of engaging all the members of the faculty on their support, or I suppose theoretically in this case, otherwise, for his appointment as Deputy Dean. And so I had a wonderful opportunity to get insight into how much Zeni means to this faculty. Every single email that I received from almost all the members of the faculty were glowing in support and showed the high regard that the faculty gives him. He's currently the Vice President of the South African Chemical Institute. His term will end in 2023, but he previously served as Chairperson of the Eastern Cape Coordination Committee of the same and the Executive Secretary of that institute for 2 terms. He's also a member of the Catalytic Society of South Africa, the International Association of Advanced Materials, and the Royal Society of Chemistry. Zeni is passionate about learning and teaching. He has done some postgraduate diploma courses in higher education. He's currently teaching from second years through honours and all the way to doctoral students. He's an NRF C2 rated scientist, has been so since 2015. He has a Google H index of 19 and an I-10 index of 40. The focus of his research, as you can see in his title, is evidenced in the publication of 98 research manuscripts, including articles, communications, reviews, 4 book chapters, and he also has 2 patents. He has co-supervised or supervised 18 MSc and 10 PhD students to completion and mentored 6 postdocs. He's presently supervising another 3 MScs and 5 PhD students, and he has 4 postdocs in his laboratory. He's guest editor for the Journal of Minerals, and he's currently editing a 2nd volume of a special edition of Recovery of Precious Metals, Rare Earth Elements, and Special Metals from Spent Secondary Products. He has received many awards. The Raikes Medal from the South African Chemical Institute and the International Association of Advanced Minerals Scientists Medal were both awarded in 2016. And of course, we have at NMU awarded him the Research Excellence Award in 2015. He collaborates with several institutions, universities, nationally and internationally, ranging from Rhodes University to the University of Florence in Italy, all the way through to Russia, South Korea, Finland, and in some of those countries he also has industry partners, some as far as Denmark. His total funding received over almost 2 decades of research is close on 20 million rand from different NRF streams, the MRC, THRIP, and industry funding. And these sources of funding are both local and abroad. Most recently, he received a grant for an August 2022 start date from the Federal Ministry of Education and Research in Germany. This is through the Helmholtz Zentrum Berlin for the consortium. This project is a UCT, Catalysis Center project, that he is collaborating with. They will be producing green gas from carbon dioxide. NMU has been awarded 5.7 million of this funding, of this consortium, and he will lead our project, our component to the project. This brings currently his total research bill to 26 million rand. This has been attracted for research from when he was at Rhodes all the way through to Nelson Mandela University. With such a brief biography, it is an absolute pleasure for me to invite Zenixole Tshentu to deliver his inaugural address and to assure him that the Faculty of Science has the highest regard for him on this day. Thank you, Zenixole.
Well, thank you so much, Madam Acting Dean, for that introduction. I'm looking for my laser pointer, if anybody can assist before I begin. I had thought it would be here. It looks pen-like, please, if anybody. Now I'm really going to panic. Okay, let me continue. Thank you so much again for that lovely introduction. Really, I'm really humbled by those words and the confidence of the faculty staff in my abilities to lead him. Thank you so much. And of course, I'm also humbled to receive this honor from Mandela University. I mean, it can be a very lonely journey to travel to be a professorship, but it's a rewarding journey at the same time. So I'm very thankful to this university. And let me now start to delve, but good evening, everybody. I am sorry. I'm panicking. I think the point thing made me panic that I won't be able to deliver this. Now I can deliver this. So greetings to everybody, of course, the VC, the DVCs, the academy, and students, staff, support staff as well who are maybe online, and of course everybody, collaborators who are online. Thank you for journeying with me. I will share a little bit of what I've done over the years and pose some questions that are still standing and perhaps where we should be, not just in research, but probably as a country as well when it comes to this. So I'll pose some of those questions. And of course, welcome to my family as well. I see my troops are here. Okay. I knew that I'm not well today, so I brought a busy slide to keep you busy while I get myself ready. Just when I was preparing for this talk, I actually got an invitation from Professor Song to join the editorial staff on this new journal, Minerals and Mineral Materials. And when I read his editorial, it sort of fitted in with what I want to talk about today. So I thought you might enjoy it as well. So he's raising challenges that, we are dealing with quality that is going down when it comes to minerals, but yet the quality of final product expected is quite high, which means something needs to happen, which means somebody needs to be working. So it means one needs to be developing new processes, even equipment, even chemical reagents in my case, to deal with these situations. Because if you deal with metal ions in presence of other metal ions, it's a very difficult situation. And if the problem is even more complex because of the low quality of the starting minerals, then the problem is even bigger. And then he talks about mineral materials or functional mineral materials. That is, we can make other high-value products from a cheap mineral, which is exactly where we should be, considering that our country is endowed with these minerals. You will see some stats. In fact, when you see the market stats and what we supply the whole world, you might not believe where we are today. Okay, but before I delve into this topic, I need to thank a few people. If Professor Dupré was not at this university, I was on my way to UCT to do chemical engineering after my degree. You see, my father likes to see you close by. So he insisted that I stay here, and he watches over me. He does that to the brothers as well. So he believes if he's watching you, then you're going to do well. So now, I was accepted at UCT for Chem-Eng. Of course, he didn't like that idea at all. So he must thank Professor Dupré that I actually stayed. He's the one that actually gave me the light while sitting through his lectures, and then he started recruiting me to do honors in chemistry, and eventually I agreed to it. And I don't regret ever since. And of course, Tommy was my supervisor, but in honors, I worked with Jan Dupré. But I mean, I was in the company and tutorship of these colossal figures. I even worked with them. If you want to see what I looked like when I was a junior lecturer out of PhD. You know? And of course, I cannot forget colleagues in the lab who are bounced ideas off from time to time. I remember Vincent would need time off the lab and decide to go out and relax, but all we would talk about all night is chemistry. His reactions that are not working out, my reactions that are not working out. So it did not help for us to commit not to talk about chemistry. And of course, these HODs that I've been through, I mean, Professor McClelland was my first HOD when I was a junior lecturer, and he trusted me to do the job, you know. And Professor K actually gave me a lot of advice. I think when I got to Rhodes, I was sold on just focusing on metals, how we use metals in medicine. I didn't want to hear anything else. And sort of got ideas into me, and I kind of understood. I might not have, I was very happy there, but I sort of broadened what I was doing because of him. Prof. Davis Coleman also energized us quite a lot. We were very young staff, all of us. He was probably the most senior, because Professor Toto joined a little bit later and then became my HOD after Professor Davis Coleman. But he harnessed what Prof. Davis Coleman did. He put a strategy to the chem department. We all knew what we needed to do, and so we could flourish. Of course, the distinguished professor on the other end always encouraged us to publish, so I cannot forget that. And my family, of course, for giving me the time. My wife here and my kids, she always says I'm fence walking in the house when she doesn't know where I am and what I'm doing. She says, I see you are here, but you are walking somewhere around the fence. So give me more fence walking, dear. I need it if I'm going to stay in the academy. So thank you so much, Ngobengok. And of course, we were a blended family. And my son there is taking, is moving the route I had traveled. You see, this was me in high school. He's on the route to become a son of the leopard. But he must finish matric there to be the son of the leopard. You can't stop halfway. So that's all way too. And of course, I did not always go to the college. That was only in the early 90s when it was possible to do so. So I had been elsewhere, of course, my primary school in my village where I stayed with my grandmother, and then a junior primary school before going on to Graham College. So, but of course, this is a post-1994 legacy that if you had to see where we studied, it's pretty different to that. I did my sub-B in Madrondava. So this is a post-1994 legacy. Of course, I cannot forget my parents who ensured that I got the education that I needed. The VC has already thanked them, so I'm not going to add to those. Thank you so much to my mother. Tolelengo, that's what we say when we praise elders. And my father, of course, Johel Kul. So we praise our elders with their clan names. Right, now I wanted us to start actually by looking at some of this. Of course, we can't separate politics from economic growth. So if you look at that, it tells you something. That something happened in the 80s, and we know what it is, right? And it has not recovered from the state that we had previously when it came to minerals and mining. The contribution has decreased. In fact, if we even look at another picture, it tells us an even bigger story of what mining was contributing to the country's GDP to what it's contributing now. But of course, other areas, other industries have grown. So, but maybe let's start from the beginning. I think because, I mean, throughout our whole lives, we've always been linked with minerals. Even if we go to the old world, how we've developed has always been linked to the riches of our earth. And to where we are now, I mean, we've come a very long way. I mean, we can go through all these old worlds up to even Iron Age. And of course, Africa is also incorporated in Iron Age. I mean, there are literature coming out of Nok culture where iron smelting is known to have happened in the Western Africa and also in East Africa around the Sudan area. So you can see, I mean, these are thousands of years BC, but people were making tools for agriculture. And so not just that, I mean, also in medicine, people were using metals in medicine some thousands of years BC. Even though they didn't understand how they functioned at times. So which means we've always relied on the minerals. I mean, if we take a leap to today, I mean, everything that we do around us, I mean, your cell phones wouldn't function without these precious metals. All these high-tech technologies would not be possible if the minerals couldn't be purified to the level that they can be purified to today. And of course, some of these functions are very widespread. I'm just sharing a few here to make things like glass. You need these platinum group metals because you need high-temperature operations. And so if you're going to work at those high temperatures, then you need equipment that can handle them. And these metals can handle thousands of degrees Celsius, no problem. Most recent and quite popular is the catalytic converter industry, where a lot is going in there, even in South Africa. A lot of platinum has increased that actually gets processed here in South Africa in the catalytic industry. But let's just simplistically look at this, because I think the problem mostly is that we look at this as just a single concept. When we talk beneficiation, we're thinking extraction and just refinery of the metal. But we need to think beyond, because that is what our country hopes for. I mean, it looks at it in several stages up to making final products. which have higher value, which is where we need to be. We are not quite there yet, but that's where we need to be. We can discuss this topic. In fact, former minister puts it like this when this question is posed: if beneficiation is necessary in South Africa. That is what he puts. That if we fail to decisively pursue beneficiation, we will relegate SA economy to a place at the bottom of the globalization of labor. Right? And of course, something needs to happen. I mean, I remember myself being in the Bahamas looking for nice earrings for my wife, and I got to a jeweler who was trying to sell me diamond rings, and of course I could not afford them there, but they tried to convince me and even showed me the process of the diamond cutter making the rings. I said, where are these diamonds coming from? She said, South Africa. Okay. And this Tanzanite, Tanzania. Okay. And so you can see the market and the forces of the economy, but that's not what we want to discuss today. Perhaps I could just throw in at the end maybe some of my own views of how South Africa can progress from where it's at this stage. Because indeed, we are the largest producer of the platinum group metals in the world. I mean, in the Bushveld complex, your Northwest and your Limpopo region, even Zimbabwe in the Great Dyke, have some reserves, but we hold the biggest reserves, over 80% of the whole world. So there should be no conversation about these metals without us, you know? And if you look at these markets, they tell you the same thing. Look at the supply by region. Look at South Africa. It's by far to any of these countries. But that's not what we want to talk about. We want to talk about the basics of chemistry. Of course, as I've said, some of the stocks that you have are not so good. So typically in high school, you will have this kind of diagram given to high schoolers about refining minerals. But little is told to them how complicated each of the steps is. They just get this simplified diagram. But of course, there's many ways in which you can do the crude separation of the important mineral from the waste and then get rid of gang. In case there's questions now that we should revisit those because there is some valuable metal still left in those. And of course, the step where we are focused in is there. It's a question of how do you separate these metals effectively, is where we are. We want to clean up and produce clean product. And in that way, you can then make other valuable products from that. I'll touch on some of the valuable products that we have made. But of course, solvent extraction and ion exchange is where we have engaged. But ion exchange is much more popular because it's much cleaner compared to using solvents. But let me just share some things. Maybe we'll ask some questions along the way. So obviously, if you're going to do this, it requires your thinking cap on right away. You know? Because there's a lot to consider. You know, who are you dealing with? Who is this metal? What is this character? And who is the ligand? Who is the extractant? Who is this reagent that's going to do the extraction? I'm just sharing here a known extractant, which is your Lynx reagent, which is known how it functions quite fully. That, of course, it's a bidentate ligand. It reacts with the oxygen and the nitrogen, but it forms this extra ring through hydrogen bonding on this from this oxime group. So in a sense, it forms a very stable compound in the end, which is microcyclic. But it's got its challenges because, I mean, you look at these need a relatively high pH region to remove these hydrogens. They're not very acidic, so you are going to separate at a relatively high pH, which means you need to get rid of other things first by precipitation before you get to that pH. So that's why I'm raising all these things. Who is the metal ion? What is your pH like? What are these groups like? What can they handle in terms of their basicity or acidity? You know, what are the constants of binding this thing? What is the association constants? What are the kinetics? Donarity, donicity, denticity. You've got to deal with all of these things. A question of who is it and how many are binding there. What is forming? What are the kind of structures that are forming when this happens? And what are the other things in solution doing? So you've got to put your thinking cap around all of that. And of course, I'll just share one or two of what we've done here. This was a very nice paper, I thought, you know. So did other colleagues think. That this extractant functioned very beautifully because you don't, a separation of cobalt and nickel is not an easy thing to do. They are close to each other in the periodic table. Property-wise, quite clear, quite similar. So you can see we did this by solvent extraction first, and then we tested if also on a resin it would separate the same thing. You can see between the cobalt, which is the squares, and this, we've got a huge pH range where we can actually extract nickel nice and pure and clean. Your problem is just copper, which is strange. Copper should be on the other side. If we go by stability, by Irving Williams, copper should be on the other end. And so we can reproduce this. You can take a material, put it through a column, separate these metals. You can even just take these four that are quite close. And of course, you can get these ones out, your iron out, and your cobalt out. They are not involved. What is involved is your copper and this, if you do that at this pH. But you can then strip the copper off and then take the other one clean. So that's what you need to be doing when you separate metals. But to get to that level takes time. In fact, it's trial and error if you're not going to do it smartly. So we are proposing other smart ways in which this can be done. But of course, this can be explained beautifully in terms of chemistry. We could explain it just from stereochemical preferences. What is forming in solution when this happens? Even what is forming in the solid state, you could understand why copper is not on this end, but this end. Because it forms a strange compound which picks up water. It's not as strong as this complex here. And so it's also not readily extractable. So you can explain all of this, and from basic bonding, but we're not going to go that route tonight. Let's tackle another difficult one. The platinum group metals themselves. Now, you're not talking metal ligand. You are talking cation-anion interaction, which is even much more difficult. And of course, this is just typically a typical flow sheet. It will differ from one company to another, of course. But let's just focus on the platinum and the iridium here, how we can get platinum out of the other platinum group metals, and how do you get iridium out of rhodium. It's just the two examples I would share with you. One we've published recently. You can readily see now you're no longer talking metal ligand. So those are the principles I was talking about of who is this metal, what is the pH like, and who's binding, where, how. You're now talking soft interactions. You're talking hydrogen donors to the electron density that's on the edges of that. This is just one example that worked. I'll just share the result quickly, that if we take a spacer between those nitrogen centers that was these two cationic centers here, if you put a spacers in between, just to accommodate this pre-organization, there's this issue, there's this energy issue that has to happen, you see. If a molecule changes shape, there are energetics involved, so you have to tune that. And of course, if you make it work, you can actually do a clean separation. This cleanly shows you if you've got rhodium and iridium. Let me just take the best one that works. Even if you overload the iridium, of course, what you overload will come off, and what is not loaded does not stick at all. And then what is in the column you can recover later. You can readily see this tells us something, that it is important how that pre-organization takes place. And of course, we have mapped it as much as we can, chemically speaking, all these hydrogen donor bond interactions computationally using a relevant level of theory, of course. And if you look at the energetics, this issue of structure energy, it actually says even if you continue, it should get better. Let me show you the results, energetics. It says if you continue to make it bigger, it should be okay. It's much more favorable. The more negative it is, the more favorable it is. And that is coming from an entropic term. So the more positive this one is, the better that is. So you can see enthalpically it's actually decreasing. So we're now obsessed with this idea. We thought you need to use rigid molecules to do this. But we're using flexible molecules, and the structure of energy, structure relationships are telling us something. So this has nothing to do with the energetics. It has something to do with the kinetics. There's just a barrier to the organization, which is kinetic in nature, not thermodynamic. It's kinetic. You can see that is after these two, this one, that is that one there. So the issue is not in the energies. So while you think you've got to lock these things in, I'm just giving you an example of what's out there. And that these macrocycles and these cages or these cryptons are probably the best way to lock these anions to arrive at the selectivity you are after. What we are proposing is that actually it might not be the case that you need not necessarily do that, because we're showing with our data that some flexibility is good, entropically speaking. But these would be your questions. If you had to deal with these, obviously, you will be going against Hofmeister even. Colleagues in biochem would understand Hofmeister bias. That these anions would be heavily hydrated, and so therefore it should not even be possible to displace, if you're in HCl medium, to displace a chloride with these things. But it's all on those interactions and shifting the energies that make it possible. So I think we are convinced that it's not about rigidification. Let's not make it too rigid, this. Because the molecule will find itself the best pre-organization, which gives you best favorable interactions. So all we are doing is assisting these molecules, is to say, all right, if we put in something, then we pre-organize it itself. We know it must bend a bit. So if we put in groups that are going to force it to bend, then we lower some of the energy needed for the pre-organization. That's an energy loss. The change of shape of the conformation, that's an energy loss in the process. So we force it to do that. We say, all right, we give you groups that are going to force you to pre-organize in a particular manner. So rigidity is not necessary. Let's work with flexibility, but let us allow it to form nice pre-organized structures without a lot of energy loss. So all of these energetics just map that. That if we can start with this and just put some groups on it, we drop those pre-organization energies. And energetically speaking, we get much more favorable energies, even on the entropy. It's positive. You see enthalpy with this particular system It's not even negative, but it's your entropy that is giving you favorable reactions. So, after all, this is a foreign concept to others. But this professor talks about it very nicely. Yeah, you think you need a delta H. I mean, the chemists here, the physical chemists, they think you need a good delta H. Yes, that's what Professor Hlangothi is saying. You need a good delta H. We're showing you don't necessarily. You can play with the delta S. Schmitten knew about this long ago. Before I read this paper, the title had shocked me a bit. He is the sign to resign from design. I thought he's saying what we're trying to do is impossible. Let's just forget about it. But he's pointing to exactly that. Here, finally, arguments to include various facets of associated entropy are presented that were unraveled by recent experimental studies. As a conclusion, the necessity to consider entropic influences in host design is emphasized. To add, although this adds to the complexity of the design task, an optimistic prospect for success is voiced in view of recent progress in computational prediction. It's probably when you need to be. If we talk drug design got there a long time ago. Of course, the big pharmas knew that it's going to be big money if they can design drugs from a rational point of view and to design tools that can do that. That's what we need to do here. We need to cover as much chemical space in terms of data and even computation and start to build models that we can just plug things into a computer and understand what we're doing without having to go through trial and error. Because the whole thing is complicated. And of course, they don't just, the energetics also work. Let's look at that. We can grab platinum from those ones. Of course, I didn't show the energetics for that and that. I focused for the platinum for that particular flexible polyamine. You can get rid of the other ones, platinum sticks, and you got to remove platinum later. If you get it right, it's all in the energy, it's all in structure energy. You can do this on any kind of material. We've done this on any kind of material. It's a bit of complication on this end that I don't want to get into at this stage. But maybe what we should be asking is what can we do with these things? We know the industry is there. Of course, the industry is not very flexible. It's always interested and not interested in new products because it takes time to get it into their system to work. But we've got lower hanging fruits. We've got new things that need to be done with the new things because the industry may be a little bit back in terms of where we are research-wise. We've got city treasures. Show in your garage, the prof sitting here, I've got lots of electronic stuff sitting. I've got stuff. I've got cell phones in my drawers, stuff in the garage. That stuff needs to come back. We need to think circular economy. What you use, you have to reuse. If you can't reuse, you recycle. Getting it to landfills must be the last thing that you do. That is where we should be in the 21st century. And given that these metals are non-renewable and they are scarce. So we're trying to see, all right, let us work with stuff that's not active because it takes a while to work with industry and it takes time and it takes building a lot of business, a lot of documents, business plans. Why don't we work with the industries that are new in South Africa, that are trying to do this without much support? Because if we recycle these, they come back and deal with the supply-demand issue that is a problem when it comes to these. And of course, I visited myself the city. Not just this city, you can go to any city and look at what the metal recycling businesses are like. Should they be like this? No. There is no safety gear, which means something needs to be happening with these industries as well. Let alone that I'm proposing closed-loop recycling systems. We need to start from the bottom, because these city treasures contain a lot of product. You can look at these yourself. So if it can be done systematically like it's done overseas, I mean, the US is there, Europe is there. We want to be there, but it's got its challenges, of course. Professor Fente here can tell you his car, he got to his car and his exhaust system was, which means something is happening in South Africa. Stuff is happening, but it shouldn't be taken from our cars, of course, while they're standing there. It also happens in the first world countries, the same problem of theft of these important metals. I've got some of them in my office as well. I just don't come and break into my office, though. So you can see these city treasures have got a lot of this stuff, and this stuff needs to come back to the market and be processed properly. So, which means processes to design these are very important. I mean, this is what we were writing about in this review here. We're saying this needs to be done, especially in Africa. Look at what's happening in Ghana. It's a kind of recycling that's happening in Ghana. It shouldn't be done this way. And stuff shouldn't be dumped like this. So, obviously, these recyclers, of course, they get a lot of aluminium here and make pots and stuff, but it shouldn't be done this way. There's a lot of work to be done. By us simply producing some of the basic methods to do these things, we can actually, in fact, we're starting to work with a very small company, MT Waste Solutions, which is in Stronde. They've got already license to trade in PGMs. So we are saying, okay, let's start small. Let's play with what you have and see where we can go. So hopefully we can get somewhere with them. I think they came across this particular paper that we had written with Puleng, who was my postdoc. Because we've been playing around with these reagents, we want to start working with them with real things. I mean, you can take these cakes out of the catalytic converters and process them and get, valuable product and separate it. And of course, those showed, of course, we understood this would be palladium selective, but all of these showed selectivity for palladium. That's a story I was running away from earlier here, that I did not want to explain certain things. But we understand why it picks up palladium at the pHs we're talking about. But we don't want to implement such high-end technologies for local recyclers. We can look for selective precipitation methods, so that if we have to do resin technology, it's the last thing we do. We would like to do simpler methods with them. And of course, we can also, with the reagents we are developing, we can also recover these minerals, these metals from waste in the mines, because there's a lot that gets lost there. It gets lost because the processes are not efficient. What I was describing earlier, you need to start to develop more efficient processes, because processes are not efficient, then you get a loss of some of these important minerals. So what we're proposing is, let's make scavengers. Let's make membranes that can scavenge these things. And of course, China and Russia are specialists at making these iron tracks. So they can use swift, heavy ions to make these iron tracks on a material, but ours is to put in the chemistry to catch what goes through here, because this must operate under very high flux, because you're dealing with large volumes, so you need to be pushing lots of volume. So as you do that, you need to have the chemistry to capture what's important. So that's what we're doing currently with the Russians, and my students haven't been able to go there for a year or so now, but pretty soon, once we can get over the problem of chemicals, VC, we have a problem of chemicals we can't get in the country. Can't understand. You know? Why don't we just make them ourselves then and sell it to the country? Some chemicals you just can't transport from Europe or wherever here. So which means now I need to get my students perhaps to Finland to do what they could have done here first before they can go to Russia to do what they need to do there. You know, when is a student going to finish with all that kind of planning? And so that's where we are. We're saying, all right, let's not lose what's in the waste. Now, the industry would probably listen to this because it's something that they battle with. They battle with also what is toxic in their waste, which can't be discharged readily. So we could design these to capture not just the valuable metals, also the toxic ones, which is where we're trying to do now. Okay, if I had time, I would have taken you to functional materials. Let's leave the first aspect of cleanup of metals, which is a difficult task itself. We were not always there. We were not always there. We were always making value-added products from other minerals. For example, we were making vanadium compounds with Professor Frost for diabetes when Sasol found me and convinced me to use vanadium as a catalyst. Sometimes your direction shifts, somebody else shifts it, and you just got to be malleable. And I don't regret it. I'm actually happy that I listened to the gentleman. I will not have time to work through this, but the problems exist. And the problems are because of course, the bad stock that you get of your crude oil, which you need to clean up. So that was the Sasol issue that we had to deal with. We had to deal with the sulfur in fuel. And of course, the legislation is there, which is a problem. We're still at 50 ppm, of course, wanting to get to 10. I'm not going to go into the mechanistic aspects of how this takes place, but I want to thank this gentleman for convincing me to go in there. Nirnel. I was not convinced, really. I was loving vanadium. I was thinking chocolate bars. Maybe you can make chocolate bars and put vanadium in it for diabetes. You know? This gentleman was taking me to crude oil. The stuff is, you know, it's dark, it's gunk, it's not nice. You know, I was used to stuff which has color, that's nice. So sometimes somebody shifts what you're doing. And of course, it was then interesting chemistry once I was there. I mean, I had a PhD student who was sponsored by Sasol. In fact, my first PhD student. And we've done a lot there, but I just want to summarize. We've done a lot there up to showing that actually these oxidative methods work. You can oxidize the sulfur compounds and extract them out. But of course, the industry is not ready for that. So I don't want to go into this whole lot of data of how we've done this. And of course, some things are just too high-end. I don't think the industry is even ready for these kinds of materials we are making. These are nanomaterials, much, much tinier. You know, your hair is 1,000 times smaller than your hair. So the industry is not even ready for these kinds of materials. But of course, we've done a lot of basic chemistry with this to understand how this happens. But I think what we're proposing is actually industry is not ready for it. Where you now need to add an oxidation and then a separation step. You have to oxidize the sulfur and then remove them. I think Peter, every time I went to present at Sasol, he would give his comment. Of course, he's on the hydroprocessing side. He's not looking at that. He's looking at we need to pump hydrogen, pressure and temperature into this thing. But of course, you compromise the fuel spec when you do that. That's the problem. You can't go very far. And so we transformed a bit. We said, all right, do mild, yeah, then you don't compromise the fuel, and then still go for the oxidation and removal. But no industry is ready to add such a lot to that. But Peter sort of pointed that we probably need to still be here. Let's not leave this. And look at the kinds of materials we are producing. What we're saying is, all right, you need molybdenum is the first thing you need, because your sulfur is going to attach to the molybdenum. But we're saying these promoters, when you sulfide this molybdenum, you put sulfurs here, protect this guy, and then bring them in later reductively when you do the sulfidation. In that way, then you get a much more active catalyst, because you end up sulfiding that rather than that when you actually make the active material. Look at that. You end up sulfiding the cobalt if you don't do what we are doing now. Let's protect the cobalt. Look at how much of what is active forms. Much more. And Spumi did this, deconvoluted all this stuff to show that. And it works, it works. But of course, but we want to do more. We put much more metals, even the platinum group metals. We say, what happens if we put rhodium in there? Will it be better? Yeah, in the one where we don't even protect the rhodium, it's actually better than the cobalt. But we protect rhodium, something wrong happens, which means we need to figure out what is happening in this chemistry here. And so, of course, in this industry, a lot of people in this industry believe in the hydroprocessing part of it. But we think that there are other problems to this. We think the stocks themselves need work, that they've just got too much nitrogen in there, which also causes problems in the reaction. So this is what we've been proposing in this. But of course, eventually the people in the fuel industry understood what we're saying. That we're saying remove this nitrogen, which is problematic in there, because there's nitrogen compound in addition to those sulfurs, and we're even providing these kinds of adsorbents you could use. They're even recyclable. A PhD student of mine demonstrated this. In fact, he's working on a Sasol feed now, which is creosote, which is liquid oil made from coal. To say we can take out these nitrogen compounds first before we process this. Maybe it will be more efficient. These are some of the solutions we've provided here. But I think where really we would like to be, which also in that particular review, we are saying that we need the mix. We need to start mixing to the renewables. And so with Gary here, we are saying, let's just take biomass to oil. Let's just make it renewable. Let's take biomass to oil, and then let's clean up the oil. In that problem of biomass, the problem is oxygen. It's no longer the sulfur. Maybe a bit of nitrogen, but the problem is no longer the sulfur, it's the oxygen. We can develop stuff to try and get rid of the oxygen, which is the exciting path we're going to travel with one PhD student and one master's who are already registering to go into this. But here is the project that we were talking about, the one that's led in Cape Town. Here we are involved in the last step. All these steps will be green. It will use, solar to break down CO2 to CO, and hydrogen will also be produced in a green way from water. So all of these steps will be green. So in a way, we keep carbon just cyclic in the system, just contributing to carbon offsetting strategies. So this is where we want to be, VC. If you ask me where I want to be, I want to go green. I want to move away from I want to move away from these fossil-based fuels. So if I develop any catalysts from these metals, these mineral materials that we make that are functional now, because a lot of work goes into making it do what you want it to do. It's also a task on its own, which I'm not going through here. I'm skipping through how do you make this catalyst do what you want it to do. I'm not going through that. So literally, that's where I want to be. But I thought I could not end this presentation without showing you this. This is what got me to want to work with metals and medicine. But I was malleable along the way because of Sasol and other funders who convinced me to move into other things that I'm enjoying. It is this. You can see the level of development affects a lot. I mean, you can see here, I mean, the high-income countries, the life expectancy is higher and higher. The infant mortality is lower. You know? And this is where I was. So I thought I would end with where I actually began, which myself and Professor Frost worked on some vanadium compounds. Also, there's a thought process there. Who do you bring in to bind with vanadium and why? Because these things are just prodrugs. That's going to break apart. You just need it enough to be intact in the stomach and in the intestines, and it must just release the vanadium. And colleagues in biochem will, of course, understand this. If I'm saying vanadium in a form of vanadate just inhibits the protein tyrosine phosphatase, you know? Because that's the one that inhibits that signal for these to be phosphorylated, then the signal can go to internalize glucose. So if you bring in vanadium, it's about designing the compound right for it. At the end, you need vanadate, which looks like phosphate. That's what you need in the end. So we're designing these compounds, and of course you go a certain way as a chemist, but look at how nicely they've worked. Look at metformin, which is a standard drug. Look at the vanadium salt just on its own. Look at the compounds. They also help with that. Also with coagulation. I mean, if we talk of diabetic patients which suffer from blood clots, we've shown that these compounds prevent D-dimer formation. Which means your fibrin stays intact, it doesn't degrade. And we've shown a lot of things. That's why I was excited back then. I just want to end with this particular one. Nano in medicine. We debate with microscopists whether this nanoparticle is in the cell, outside the cell, in the cytoplasm, in the nucleus. It's a nice debate, but for us, we can make these things. I mean, we can. We know how to make them in the process of making higher value products. So I think that's what I'm advocating here, is that a lot can be done in making higher value products. I think I must summarize. But this question of endowment, of mineral endowment versus competitive advantage, we cannot leave behind. As to where we should be as a country, I don't think we are there yet. There's a lot that needs to be done. Maybe on the platinum, when it comes to catalytic converters, maybe a lot has been achieved. From some 2% that was used internally in the early 90s to about 10% now that ends up in the auto catalyst industry. That's some improvement. But we need to start small. I think South Africa is looking at big things. You know, we need to start from basics. Like I'm working with MT Solutions from Strondale in KwaZulu. You know, we need to help him to say, how do we get pure product out of what you've got? First, how do we get it to a powder that we can process and get pure product? We need to start from basics which don't need a lot of capital investments and get people moving on their own. I mean, South Africa has a lot of titanium, and there's potential there to beneficiate titanium. I don't know why we are not in the chemical sector and other higher-end materials and biomedical sector. All these dental materials. A lot of them get made elsewhere and then they come. We have a lot of opportunity to get involved in the energy security sector for the country. The hydrogen economy should be booming. Fuel cell technology is showing promise. We've got the materials to do these. But of course, we remain here as a scientist. We're still committed to make the methods work. And of course, we are also shifting towards making mineral materials that assist with issues of climate action and circular economy. So that is where we want to be. I would like to think that I would have convinced you that actually merging basic chemistry and applied chemistry is the way to go when you deal with these things. You can't leave the one and then work with the other. So we do both to ensure that we get where we are, because for us, every molecule matters, so how we make it matters. And of course, I would like to then thank a lot of people who have worked with me on this journey. Antonio Bianchi, those energetic issues of those ion outer sphere coordination, he's right there with me, and my students. And of course, Prof. Frost and I have worked a lot with metals and medicine. I remember spending time in Prof. Chon Kina's lab in Korea for about a month, trying to get ligands onto materials that we cannot make. We said, okay, let's use graft polymerization. And he provided solutions for grafting some of the ligands onto the materials that we wanted to make. And of course, there's many, many more. Of course, Nelson and I also did a lot of work at Rhodes on functional materials. And Dr. Parajuli in Russia, currently we're editing the special issue on recovering this from city treasures, the special issue we are working on. And of course, Jack from the UCT Catalysis Centers, we're poised to get moving. A lot of infrastructure is going to come in to get that project on the move. And of course, postgrads. This is Ryan, who was the first PhD student at Rhodes. Ivan here was my first master's here that I co-supervised, actually. And I think Mr. Okowoli was my second PhD, followed by Sunday over there. Now Sunday is my age already. Some of these guys were associate professors with me, actually, which is amazing. He's associate professor, she's associate professor. They were always asking me, Prof, when are you going to be promoted? When they became associate professors. I said, it's not about that. And of course, some current students here as well who are working on some of these many problems. And of course, the funders who allow us to be able to do the work and use some of their materials as well. I mean, Aldo Topso provide us with some of their catalysts to benchmark with what we make, with what's out there in the industry. And of course, I thank you at this stage. And those online, of course, for bearing with me through this presentation. I thought I would struggle to get through it because I'm not feeling very well, but thank you to everybody.
Of course, one of the big mysteries have been solved in this brilliant lecture. That is what has happened to Prof. Venter's car's exhaust system. Now, of course, many of you would know that it's, in fact, my brain has been disembodied from myself through Zeni's presentation, and it's very difficult to follow, the complexities of such great work. Zeni, but we tried very hard in that corner, okay? Very, very hard. And we can get some award for effort, at least, on this. But I think that we get the social and scientific value. That sense of your work is clear. So, Prof. Tshentu, it is my privilege to congratulate you on a captivating inaugural lecture where you shared your thoughts on how to move towards mineral beneficiation from basic chemistry to applications. Your argument on the importance of the development of methods for recovery of metal value and the further beneficiation strategies for utilization of mineral products, in value-added applications are compelling and instructional. Especially that last slide of yours where you pulled everything together is testimony to that. It is undemanding to imagine the great social and scientific value of your past, current and future work, not only for our country, but also for our continent. Your intellectual labor is of immense importance. So thank you very much. Please give Prof a hand. As your work and that of your colleagues center around both basic and applied chemistry towards mineral beneficiation with a bias towards greener production, you are also responding to our current planetary challenges. So congratulations and best wishes on your career further and with the task lying ahead, and of course your ambitions that you have shared as well, especially intellectual ambitions. May I also express the gratitude of our university for your contributions over many years, Zeni, and especially relay the thanks of our Vice-Chancellor, the Executive, and our Governing Council. I would now like to take the opportunity to share a message with you from the President of our Alumni Association. Dear Prof. Tshentu, congratulations on your inaugural lecture. The Alumni Association looks forward to your support and involvement in our activities to mark this very special occasion in your academic career and your time at Nelson Mandela University. On behalf of the association, I would like to present you with this symbolic gift. And of course, the last message from the chairperson, president of the Alumni Association, is best wishes on all your future endeavors. In closing, I would like to convey our thanks to those who are attending this inaugural lecture in person and virtually. Your interest in the work of Prof. Tshentu and that of our university is much appreciated. Thanks to our VC, Prof. Mutwa, for the welcoming remarks, Prof. Campbell, the Acting Executive Dean of Science, for introducing Prof. Tshentu to us. And thanks also to Prof. Tshentu's special guests, friends and family, his wife and children, his mother and his father, his mother-in-law as well, and Prof. Gerber and Dupree as well. Last but by no means least, thanks to the institutional governance team in the office of our registrar, our communications and marketing team, and our ICT team that made the inaugural lecture possible. You did a great job. This brings to a close the inaugural lecture of Professor Tshentu. You are invited for light refreshments in the foyer. May I request the audience to stand whilst the academic procession leaves the venue. Thank you very much.